Okay. Yo, and Burrows. Incredible. Oh, there's no. It's just us. Oops. Um. Hmm. It's a compliment. Ah. Hey, Sipet, how's it going? Awesome. Very important meal. Oh, Arbitree, how's it going? Welcome. By the way, is the music playing or is it still silent like that one time? Oh, okay, that's good. Interesting. That's really weird. Okay, I think most of us are here. Let's start. Um, yeah, so before I start class, I should tell class that things are gonna get kind of busy around here. I have to permanent substitute for Calculus 3 class. And then we have our intersection theory seminar that's going to start on Wednesday. So yeah, things are going to be kind of busy around here. No ads, procrastination? That's great. It's starting tomorrow, Arbitrary. Tuesday, tomorrow, first class. 3 p.m. That'll be weird. Just come in the middle of a semester. Yeah, I've never done that before. We'll see how it goes. We'll see how it goes. Okay, but here We're basically finishing chapter 10 today, moving on to chapter 11. The main content of chapter 10 is how big is a fixed field? That's the question that chapter 10 tries to answer. Well, it answers perfectly. All right, so we're going to prove that theorem because the proof is beautiful and basically amounts to linear algebra. Okay. Hey FemFox, how's it going? All right, so let's do that, and then I'll do some much needed examples because we haven't seen examples in a couple days now. Right, important examples to get under our belt and to witness these statements that we've been abstract things we've been studying. Okay, let's begin. So here's the setting for our. Let me recall the setting. You've got yourself a field. And suppose you've got a group of automorphisms of that field. And it's a finite group of field automorphisms of K. Remember, I guess he's not here. Remember, Kappa, when we say automorphisms, it means self maps. Isomorphisms of the field into itself. Some group of them. It doesn't have to be the total group of automorphisms. It's just some group of automorphisms of K. Then you can talk about the fixed field, which I will denote as K superscript G. It's those elements in the field K which are undisturbed by the group automorphisms. Okay, you got a fixed field. And the question that we want to investigate in this chapter is how big is that field relative to the original big field? Okay? So the theorem is that the index is like finite. Yeah, some group. Yeah, okay. It doesn't have to be the full Galois group in your mind or anything. It is just a group of automorphism, finite. So the theorem is that this extension has degree the size of the group. This is the main theorem of chapter 10. It gives us a little relationship. Okay? And this is true arbitrary characteristic. No, it's like a universal, like part of the fabric of the cosmos type math. Okay? This is like super general. It's not about subfields of C. It's like completely the most general type of statement you can ever hope for in mathematics. All right. So the ingredients will be linear independence of homomorphisms, of monomorphisms, Dedekind's result from last class, and some linear algebra. Okay, that's the rough list of ingredients. Okay, so let's go through the proof. The proof is beautiful. Okay, the proof is nice. Let's fix some notation. We're gonna let M denote this thing. Okay? And we're gonna let N denote the size of the group. Okay? And we're just gonna list the elements of the group like this. The first element we'll just call will be the identity, and it'll call G sub 1, and then G sub 2, G sub n. Remember, each of these are field automorphisms of K. In particular, they are monomorphisms from K back into itself. So, since they are distinct, they're distinct elements, we get to assume. So we are in the setting of Dedekind's lemma, that distinct embeddings of a field into another field are linearly independent over the target field coefficients. Okay? Review that. Dedekind's scalpel is what I called it. Okay, so this is just some notation. And now we're gonna do two things, okay? So the strategy is gonna be to do this. The strategy will be this. The basic idea underneath the proof is this. You write down a matrix, meaning a grid of numbers. Okay, you do the following. So first, let's so you write down a grid of matrix, a grid of numbers. Okay, so let's do the first case. We're gonna first assume that this number m is smaller than n. Case 1. Suppose m is less than n. That the degree of this Hey, Eric Charneski. Yo, why are you here? Wow, incredible. Welcome. And my mods, they're not doing any shoutouts. What the hell? Yeah, hope you're having a good Monday too. Okay? So first assume that the degree is less than the size of the group. And now investigate the following, consider the following grid of numbers. Okay, so first, choose a basis of K as a K's G vector space. I'm going to call the basis E1, E2, EM. To say that this degree is M means that K is an M-dimensional KG vector space. That's the definition of degree, folks. All right, so I'm just going to choose elements of capital K that form a basis of capital K as a vector space. These are each elements of capital K. They are linearly independent over the small field, and they span. Okay? Good. All right. So once you choose that basis, you can form this grid that I'm talking about. Magic grid. You go like this. I'm going to make sure I do it right. Which one's bigger than which? Hold on. Like this. Yeah, this looking better. This must be a 2 here. This must be an E1. Wow. Did I just do this? I think I did this. My full PhD is being utilized here. Wow. Incredible. Look at this grid. Now, these are elements in capital K. You can't deny that. And this is, just focus on the shape of this matrix. It is M rows and N columns. All right. But if n is bigger than m, then this matrix has a non-trivial kernel vector, which is a vector of size n long. Okay? So then, by linear algebra done over the field K, because this matrix has entries in K. Okay? By linear algebra, there exists numbers y1 up to yn such that basically when you hit this matrix by the column vector y1 to yn, you get 0. But also these y1 up to yn are not all 0. And this sum yi times, how did I write this? gi ej no 1 to n equals 0 for all j's. Okay, so notice what you need to focus on here is which index is being summed over. So this j is any one of the j's. The same tuple y1 up to yn solves that system of equations. All right, in other words. Okay, awesome. So you get this solution vector of this matrix equals 0 times vector equals 0. This particular solution vector, non-zero. Okay, so that's something you get, and this is true for all j varying from 1 to m. It's like simultaneously true. Okay, but now if you know that this one relationship, the y's, is holding among all the outputs of the ej's, it actually means that the elements g1 up to gn are linearly dependent homomorphisms. So the claim here that finishes this argument, the claim is actually that this implies that the sum of yi's times gi applied to any element is 0. This will violate Dedekind's lemma. These are linearly independent homomorphisms because they are distinct. Oh, thank you, Smash. What a wonderful contributions making. Amazing. So, why is this true? It's because the EJs, they span the large vector space K, right? Because, let's see why this is true. Because X can be written as a sum of xi's times ei's, where xi's are in the small field. Right? The ei's were a basis of the large capital K as a kg vector space. So you can write every element like this. And now if you apply, for example, gi to that, or maybe not I, gj to that, gl to that. Well, the G's are field homomorphisms. So they distribute across sums and products. And so these individual sums get placed right here. And then you just distribute across. And use that these individual linear combinations were 0 to obtain the result. So you get use this thing. To get the claim. Okay, so in fact, we violate Dedekind's lemma in this case. All right? Okay. Okay. So now we have to deal with the other case. The other situation. Oh, okay. So you place, okay, no problem. You place this sum. You place this sum here. For the elf spot. And then you distribute. Yeah, but this is x because these are just xi's. If you can simplify it. Yeah, sure. Yeah, it's a little bit of algebraic shuffling of the summation symbols. But yeah, the point is that knowing only that the yi's are a relation among the outputs like this will tell you that the yi's are a relation among every output. No, this is equal to xi because the xi's are in the fixed field. So this is actually just, these are the same. Oh, did I? Oh, yeah. GL. Like this. GL. Here. Absolutely. 100%. Exactly. And then you plug those in and you use this thing 1,000 times or something. And you still get 0. The point here. The fast way of saying this is that there's actually a fast way of saying this. It's that if you look at this map, this is a linear transformation of kg vector spaces. Just that the sum of yi's times gi's. Okay? It's a linear transformation of kg vector spaces. And you know that that they send the basis vectors to 0. It sends all the basis vectors to 0. But that means it sends the whole vector space to 0. It's that principle, but being written out in gory detail. Yeah. Okay? That's the fancy way of saying it. All right, other situation is if the degree is larger than n. What if m is larger than n. Okay, there's a slightly annoying... Wow, not prof. What are you doing sending... Wow, amazing. Not prof. Thank you. Right when I was switching cases. Perfect timing. Hope you're having a great semester. Okay. So what if m is greater than n? Now there's a small little detail that I have to like worry about. It's not actually clear that at least at first, that this side is finite. Like, is this infinity maybe? Not exactly clear, okay? However, you can reduce to the finite case of m by just, in the next case, this matters, right? The previous case it didn't matter, but the next one it matters. So the one way of getting around this is you just assume that there are n plus 1 linearly independent elements in K. So what if m is greater than n? So to get around we do the following. We assume E1, E2 up to En plus 1, or any finite number bigger than appropriate finite number bigger than n. We assume this is a list of independent, let me emphasize, we just assume there's n plus 1 linearly independent elements in K, because that's true. If you have that one vector space is bigger dimension than another, then you can find appropriate large number of independent elements. Okay? That's what we're using. Okay? And so we assume we have this list of independent elements in K, and the list is a little too long this time. Last time the list was a little too short. This time the list is a little too long. But now you write down the following grid. Magic grid. Requires the full power every time. Look at which index is varying which way. That's the pattern. Okay, use your pattern recognition here. Use your full PhDs. All of them. This is the transpose of the other grid. That's if you want to be fancy with your English. Okay. Now focus here. This grid is n tall and a little too wide. More variables than equations. So this system of equations, or this matrix, has a non-trivial kernel. So once again, linear algebra over K. There exists a non-trivial relationship, or column vector, that this times that column vector equals 0. You get y1 up to yn plus 1. Non-zero, not all 0, such that you get these. Such that these sums. Now let me try to write that matrix multiplication. For every single GJ, for every single element of the group, apply them to these particular elements E1 up to En plus 1. This mysterious set of n plus 1 numbers will relate them, will be a dependency. Okay? This one list of dependencies is a dependency for all the group's outputs, group element outputs for these particular elements. That's the claim. All right, so this is a, notice which index is being frozen and which one's being summed over. Okay, so you get that. Awesome. Incredible. Okay, so what we're gonna do now is we're gonna do a little bit of basically row reduction type argument to this situation. Okay, so first of all, these are not all 0. Okay? They're not all 0. Now, what you can now do is, among such solutions, vectors, y1 up to yn plus 1, you can choose the ones, or you can choose one which has the smallest number of non-zero entries. Obviously, you can do that. Then you can reorder the EIs. What happens when you reorder E1, swap E1 with E2? Oh, I'm sorry, I forgot to list them the right way. It just swaps these columns. Look carefully. Yeah? So you can swap columns, swap the E1s up to En plus 1s around so that the following is true. You can assume. The yi's have the following properties. Smallest number of non-zero entries. And 2, y1 is not 0, y2 is not 0, yr is not 0, and then afterwards they're all 0. So you put all the non-zero ones first and then the 0 ones second. Okay? So in particular, we are looking at this sum. And none of these yi coefficients are 0. Yeah, that's us. We can bring it all down to this particular situation. All right, and this is true for all. Okay, we can bring it down to this situation now. All right, and now we do the most interesting trick. We do a very, very interesting trick. Okay, I'm gonna do it some other way. I'm gonna do it my way. Okay. Since y1 is not equal to 0, we can actually divide out by y1 everywhere and assume that y1 is actually 1. Just do it. Just do it. By dividing out. Okay, we assume that y1 is actually 1. And notice 1 is in the fixed field. Just want you to observe that. Okay, but the yi's are just elements of capital K. There's no hypothesis right now about where the yi's live. They're just in capital K somewhere. So now what we do is we do something very clever. We apply a random element of the group G to these relations. Now the trick. Okay? I want to emphasize, by the way, that there are n equations on the board right now. One for each j. Think of them as like little rows. Now, I'm going to apply an element of a group to one of these equations. And let's do it. Okay, G is a field automorphism, so it distributes across sums and products. Okay, now I want you to focus on this thing. G of some other G, maybe, of an element. This is a new GJ prime. You see, because the group has this, the group operation is composition of functions. Okay? Now, the observation is that this new equation, of course, equals 0, right? Because 0 tends to 0 under field automorphisms. This new row, this new equation is just some other row in this list of n equations. Another way of saying all this is applying G to this grid just does row swaps. Swaps the rows in some way. Scrambles the rows in some way. Right? Applying G times the... If you have a group and you apply multiplication by G is a bijection from the group to itself. We're just using that little fact. Okay, so this list, applying G to it just scrambles the entries of that list. Okay, so this is another equation. Right, this here, this GJ prime is another uniquely determined and so what this means, so in particular, we earn another solution, another y1 up to yr set of numbers. We have the original one, and we get another one. We get two relationships among these elements. And now we compare them with each other. You compare them with each other by first noticing that y1 was 1, and so g of y1, it's g of j, yes, Femvox, it's g of j prime, but g of j prime was g of j if I had started with some other g of j. You see, g of j prime represents just a scrambling of this list. You're right, it's g of j prime, but g of j prime is just an arbitrary element in the group. let me say it this way. If you write these n equations down, and then for each one of them, apply g to it. For each j, you'll get a g of j prime here, in this entry right here. But write these equations on the board. It'll just be sort of a scrambling, if you focus on the g of j prime stuff, of the previous sort of order in which these n equations were listed. What changes are the coefficients. yi's became g of yi's. Yeah, it's a scrambling trick. Exactly. It's true for all j. Exactly. And exactly. So you get, and notice the great thing is that the coefficients of the new equations are all the same. They're just g of yi. They don't depend on j. This doesn't depend on j. Okay. So in particular, you get two competing relations among these g sub j ei elements. Two competing ones. The original one, which we assumed was minimal length and all non-zero entries, whatever. And this new one, where basically you apply g to those coefficients yi. That's also a relation, apparently. And now I want you to focus on the first one. y1 is 1. So look, I'm going to write it out. 1 times and you also have g of 1 is 1. 1 times. So remember, these are the same in all of these. But these are changing. These have they've possibly changed. Okay, but now you do row reduction to this pair of rows, basically. So you take g of y2 times the top row. No, just subtract the rows. What am I doing? Subtract the rows. And you get g of, or y2 minus g of y2. Notice this is for all the j's at once. But no, this is a smaller length relation among these blue things. Smaller number of, it's a smaller length relation. Yo, raid, another raid. Huh? Who's raiding? Who's raiding? I don't see it. Not prof. It was not prof, dude. Okay. Oh, you're awesome. Okay, this is a smaller length relation, which means all of these coefficients have to be 0. So these have to be 0. And so we get the following system, we get the following observation then, i.e. y2 is g of y2. y3 is g of y3. yn plus 1 is g of yn plus 1. In other words, the yi's are in the fixed field. All right, see you, not prof. Thank you. All right. So you get yi's are in the fixed field. But now, go back to our favorite relations and do it. Consider the case with G1, which is the identity element in here. What do you get? You get that this would be a non-trivial KG linear dependency among the EIs. That's a contradiction because the EIs were assumed linearly independent in the beginning of this case. Okay, that's bad. So to recap, the two cases looked at basically, you basically do this to summarize. Choose a basis of K over KG and list the elements of the group and sort of create the grid of group element applied to basis element. If the grid is too wide or too tall, you produce these relations to sort of hold on to and then meditate upon, play around with. Okay, so that's the method of proof of this beautiful theorem. And the theorem is super general. It doesn't require any knowledge of the characteristic of the field. Is it a subfield of C? Nothing. It's super at the foundations of mathematics. It's very, very basic universal truth. All right? So this is our main chapter 10 topic. We know that now that the fixed field of a finite group of automorphisms is always the size of the group away from the original field. Okay? It's giving us refined information about sentence number 2 in Galois theory. When you have the group of automorphisms of a field, and then you look at the invariance of that group, the stuff that doesn't change, how big of a field extension does that generate? Does that create? It's fine-tuned information about this concept of attaching a group of automorphisms to a field. Awesome. Awesome. Amazing. So now in the last 2 minutes, yeah, bad equals good should become an emote. I agree, Arbitrary. Our emote making studio is busy days with school. So I don't know when that would happen. Yeah, there's only 2 minutes left, NC. Well, technically. But I'm going to do some examples. Okay, I'll do our one of our favorite examples. Okay, I'll now tell you what the group I'm investigating is. Okay, so they have S3. Now, S3 acts as a group of field automorphisms of the large group. The size of S3 is 6. The degree of the large field over Q is also 6. Interesting how those match. But there's another thing. That if you look in S3 and look at the subgroup called swap, let's say, or A3. Let's look at A3. Which means do this. It's generated by the 3 cycle. This is a 3 cycle. And what is the fixed field of this this group of automorphisms of the large field? In this case, so this is group of permutations equals the group of automorphisms of this field. What is the fixed field of that? Well, I don't know. I don't know. What I do know is that the fixed field is a degree 3 index away from my large field. And there's only one of those fields in this diagram. So it must be this one. Because the size, that's the only way the sizes work out. The fixed field of a group has distance group from the large field. Distance in the sense of degree. Yes, exactly, Vixen. That's exactly right. Okay? So you can just identify what has to, and indeed, if you look at this automorphism, it has, automorphisms like this have to fix omega. No, you don't believe me? Look at this. Check this out. If you know that this is the effect, you're looking at elements like this, or this element and its square, and the identity. Then look, if alpha goes to omega alpha, and alpha goes to omega squared alpha, then where does omega alpha over alpha go? That goes to omega squared alpha over omega alpha under this, let's call this sigma. And this is on the one hand omega, and this is also omega. So indeed, this thing is fixing Q join omega. Sanity check. Okay. Similarly, there are other subgroups of size 2 in S3. There's swapping. You have a tau. Tau does this. Tau swaps, let's say, alpha and omega alpha, and keeps omega squared alpha within itself, let's say. What is the fixed field of the subgroup fixed field? Well, the theorem we just learned is that it's one of the 3 index 2 subgroups. Or index 2 subfields, or fields that are 2 degree away from the large field. So there's 3 options, but it has to be exactly this one. Because see, omega squared alpha stays fixed. And so the field generated by it has to also stay fixed, and the size fits right. This is size 2. This is the size of this group. Okay? So I'm showing you the fixed field for various groups, and we're matching them. We're sort of saying it has to be this because we know that the size of the fixed field is a particular number. Distance is index, or sort of degree of a field extension. That's the concept of nearness and farness. Yeah. Exactly. Exactly. I speak in intuitive terms. I don't speak like a book, unfortunately. Some students don't like this. They get comments like, more formal mathematics, less telling me how to think about things. Well, then read the damn book. Just read a book, then. What are you doing? You don't need classes. Just read a book. I guarantee you it'll be tough. Okay? Distance. One field is degree 5 from another. It's like a mental concept of how big a field is relative to another, how distant it is. Absolutely. Okay? So, do examples with Q adjoined square root of 2, square root of 3, where we know the Galois group is Z mod 2 cross Z mod 2, having the effect of swapping square root of 2 with minus square root of 2, square root of 3 with minus square root of 3, and then, well, what else happens? Draw the entire intermediate field diagram, which we know, and compare fixed fields of certain subgroups, how far they are from the large field that we're acting on. You'll see that this was not that our main theorem of chapter 10 was indeed not a lie. Okay? Right, NC, right. Okay. So. Now, the next order of business will be chapter 11. But what chapter 11 does is it just makes precise and states in proposition form this extension type lemmas that I emphasized before. Meaning, how can you build an automorphism of a field which has a particular desired effect on some subfield or some particular element? I want to know if there's an automorphism of the ambient field which sends this alpha to this beta. Is there one? That is the basic tool that chapter 11 develops or just emphasizes. We've already seen the proof of that tool, but it's going to sort of be emphasized in chapter 11. It's going to be zoomed in on and investigated further. And I think it's in chapter 11 that we will see where separability comes in to the picture. Okay? And once we have that chapter 11 investigation under our belts, we will then be right around the corner from proving the Galois correspondence. All right, good. So, who's here? Fembox. Vixen. The usual suspects are here. Oh, Charnesky. Thank you. Not Prof. Thanks. Thanks for the interruptions. Awesome. Who else? Arbitrary is here. Making sure everyone behaves. And of course, Smash Time. Doing something in the chat. Not clear what that is, but Smash Time is a moderator, so you have to be confused by this math. when I learned algebra. Right. This mathematics is really old, Eric. It's actually like 150 years old. So it's not some like this new math that maybe you, I don't know, were you subjected to that as a child? The new math? It's considered very, very down to earth for mathematicians these days. No. Mid 1800s, that is standard curriculum now. Yeah, integral calculus was developed also early 1800s, maybe? Developed properly. So, I think. It's 1800s sometime. Early, mid. So, yeah. Yeah, wasn't there a new math? Like, new math was placed in the curriculum in like the 70s. And it had all this like weird like set theory that people were very opposed to. Hey, who's Rams Reef? Wow, new person. Welcome. Hey, procrastinagitation, you're here. Keeping me honest. Good questions. Asker of questions. This is actually what I like about the teaching here. There's way more questions than teaching the boring way. This is now objective. Like, I've actually, in my other classes, I've switched because the students chose to. It's like dead compared to what happens on the channel, where people ask questions even if they think it's silly or small or something, because often it's not a small matter. It's part of a important clarification or something. So good. Asker of questions. NC is here. Common Core is good. It helps teach mental math. Yeah, mental math is pretty important, I'd say. Number sense, common sense type intuition building. I like that too. Yo, NC, you're here. Hey, did you know NC? Did you know NC? NC streams. Look, I shout out everyone here. Look, shout out to NC. Non-dairy. All that right? Yo, Shearshack. Shearshack. I haven't seen you in a while. Hope things are good with you. All right, later, Eric Charneski. All right. All right. So anyway, is the class over? Yes, Shirshak. Absolutely. Now, what's coming? Mondays and Wednesdays. So Mondays and Wednesdays. Starting Wednesday this week. Is BMP After Dark. It's a worldwide international seminar. 6 p.m. It's like this. You've got like the United States, and then we got over here you got a seminar. For mature audiences only. It's gonna be hard. It's the topic is something called intersection theory, and it's really for my students, graduate students, and former graduate students, and who want to learn some difficult algebraic geometry, but beautiful stuff. So that's the topic. It'll meet Monday, Wednesday, 6 p.m. Everyone's welcome, of course. But just remember that it's don't forget New Zealand. Oh, New Zealand? Oh, sorry, New Zealand. Sorry. Central. It's evenings, so that it's like the next day in the middle of the day for them. I don't know. Isn't there like a line that's like the difference between today and tomorrow? I don't understand this. I don't know how time works, but yes, that's Mondays, Wednesdays. Then Tuesdays, Thursdays. Calc 3 Substitute Teacher Edition. Permanent sub. That'll be exciting. Yeah, the students chose to do it on here. I had them vote because I didn't want to impose it if they already liked what they had. So they chose to change. So let's see how that goes. All right. That's now that'll be stream every day. That means. Will it be BMP style? Yeah. Not serious. Not serious. A lot of third eye. Return of the third eye. Because the third eye was created for Calc 3. This. Calc 3 comes back. I told Vixen, I told my brother to reset that's Sokotoa Island, right? I told him to reset it so that there's no rabid frog in the middle, because that won't make any sense to the new students. Right. We need to I don't know how to do this, but maybe Smash Time, you gotta reset confused. Because that's just gonna confuse them. If you're here, Smash Time. Or whoever. Who knows how to do this? Reset this confused command. And I also don't even know if I can get to Green's theorem in time. Because we're kind of behind. That's right, Vixen. Yeah, so that'll be fun. Wait. Command edit. Confused. Oh, check this out. I'm gonna do it. Ready? Command. Edit. Wow, look at I'm coding this. Wow, I feel really smart. Confused. Brackets? How do you say nothing? Okay, well, thank you for that. Thank you. Okay, edit. Confused. Nothing. What? Something's wrong, NC. Wow. Yeah, I want old. Just nothing. Arbitrary, just nothing. Right? I just want nothing to be stated after third eye. I mean, after confused. I don't want it to say anything yet. What are you? Who is this? This person again, dude. I'm gonna click on you. I'm gonna figure out. Okay, how do I go? 67 comments. So, how many followers? 0 followers. All right, I'm gonna follow you. I'm now following you. You know who you are. Interesting. Interesting. Yeah, it's laughing at me. Vixen, what the heck? Command is on Nightbot. So how do I tell Nightbot rather than stream elements? Interesting. These are really deep questions. Huh, maybe I'll learn one day. Okay, so now what's next? Right, commutative algebra is next. What am I doing in commutative algebra? Oh, wow. Wait, ready? Arbitrary. We're gonna do this. Try. No, not try. Command. Remove. Confused. Wow. Check this out. Yo, arbitrary, what's going on? You see this? My screen is so big, it's sort of... Format is command name, command fonts. Means what exactly? Yo, Pandemic, how's it going? That's right, Vixen. This is the easiest test. Yeah, I know. It's just some weirdo on the internet. I know. Okay, we gotta update the list of who showed up. Pandemic is here. Welcome. Docs, Nightbot, TV, commands. Yes. Is that a yes or no question? Yes. Wow. Whoa! Who did that? Incredible! Wow, good job. Good job, Arbitrary. That's like at least one competent moderator. Amazing. Yeah, I knew I made a good choice with Arbitrary. Wow. Incredible. Really? I don't think so. I think I'll get in trouble for that. Okay. Careful. All right, ready? Wait. We need to thank this theorem too. What? Class? Beautiful theorem. Tells you how big the fixed field is. Or small, I guess. However you want to think about it. Awesome. Gives you just a little bit of information about the structure of the Galois group if you know the fixed field anatomy. Tells you something. Just something. Some relationship. Beginning of several relationships. The main relationship captured by the Galois correspondence is the fundamental theorem of the subject. Amazing. But really, Femvox, that's so sweet. It's not actually, but wow, what a great comment. You know how I know that, Femvox? Femvox, here's what happens. Let me let you in on how streaming works, Femvox. So there's this thing you end stream button, and then you click it, right? Click it. Femvox, are you paying attention? You taking notes? People G? Now, you click that and you'll get an email. Goes by. Get an email. In fact, you get a Gmail. And it's straight from Twitch. And it says, wow, great job. It might be, maybe it's Femvox. Wow, great job. And then it tells you these stats. Tells you all these stats. Number of degenerates in chat. And all kinds of things. Okay, it tells you all these things. Okay, number of theorems proven. All this stuff. Okay, classic things. Number of follows. Yo, Carrot Cat, how's it going? Hope semester's going well for you. Exactly, Pandemic. That's what it says. Exactly, Ram. It says this is how bad you were. And Femvox, all these numbers have been declining for since the beginning. Femvox. So that's just how it is. Yes, exactly. 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 So on. Well, only streamers know about this secret. This is what they do. This is what they do. And then you look at it and you're like, wow, I need to do better than that. And then they hook you like that. They hook you. All right, so this is how I know that your comment earlier is false, because I literally know that it's not true from facts, science. Just basic science and facts.
Yes, science!
Yeah, we got to use more of these in my calculus substitute edition. Substitute teacher edition. Like this.
Incoming problem.
I alone can fix it.
Okay, maybe not. Maybe they're old now. Maybe they got stale. Especially that last one. Maybe I don't know if I'll use that last one, but you guys remember this one? Wait, do I have the old one? Do we have this one? Look. This is the old one.
Incoming
This is the old one.
Incoming problem. Incoming problem.
It was funny when you had to be there. Yeah, but I don't make them, Vixen. Talented brother makes them. So, I don't know. We'll see. I'll have to ask him. Maybe think of another one. Carrot Cat. Yeah, Carrot Cat. I'm doing Calc 3 again. I have to. I'm a permanent sub for another class. So it's gonna be 3 o'clock Tuesdays, Thursdays. Yeah. Yeah, those were the good old days, right, Shirshak? But yeah, I'll be reviving them for Calc 3 to increase engagement. Yes, arbitrary. Once they become comfortable, if I have enough people who are comfortable with that, I will be consulting with the generals of Discord. Arbitrary. Yes, I hope so. No, Rams Reef. I don't actually eat. I don't eat meat and fish. Rams Reef. I know, Vixen. Oh, do I like? Oh, well, I mean, okay. Well, okay. Technically, good, Rams Reef. Yeah, I suppose I do. Yes. Yes. It's an interesting conversation starter. Oh, really? Wait, are you serious? Really? Really? Like, for real? That's cool. Wait, really? You have a fish stream? Oh. Let's shout out Rams Reef. I shout out everyone who's streaming because so that maybe your emails look a little bit better than my emails. If you know what I mean. Wait, let me go look at this. Dude. You're live right now. I'm gonna follow. Well, that's cool. A utility system. Specifically the protection and controls. Shishak, I thought... Where in the semester is your Calc 3 class? Good question, Carrot Cat. I believe they are in right after computing arc length of a path in R3 or something. So section 13.3. Wow, are you Jane? No, I'm just normal Gujarati. Procrastination. Um, good, good, good. Oh, really? Really, Rams Reef? That's cool. Okay, we're gonna go. You know what? We're just gonna go. We're just gonna go to Rams Reef. All right, we're gonna go to Rams Reef. It's literally a reef, and it has fish. All right, we're gonna go there. We're gonna go there. Okay, how do I do this now? Okay, go like this. Yeah, let's go. Hey, is it? Are you? Is it science and tech? You should give him a custom animation. I don't know what you just told me to do, Ramsey. I'm not very smart, but I'm just gonna raid. Okay. I'll try. I'll read that sentence a couple times before. And I think it'll finally click what you're telling me to do. Okay, everyone, we're gonna go support Rams Reef. Why? Because I'll get a better number in my Twitch email. Who asked that? Femvox. Got it? No, but I do. It's just fun. When people in the community, there's no community here, but when people in the chat also stream, I like to go send and troll, send the trolls over there for once. All right. There, go check out those fish. They were actually very cool, actually. I saw a couple. Kind of big. Are they big? Are they as big as they looked? Rams Reef? Shishak. All right. The fish. All right. Okay. Let's go. I'll see you guys tomorrow, maybe, if you show up to calculus. Okay? All right. Thank you. Fish stream. Awesome.